with channels allocation. Okay, I'll give you a scenario where you see how this one works out very well. So don't worry about it. We'll get to that so we can see it in practical implementation. Now, channel frequencies are usually modulated, either shift and combine, through a multiplexing approach or implementation. And that's usually what makes it possible to have multiple users use one link, a single link with a given capacity for their transmission need, for their data informations, or if it's voice transmission or video transmission needs. Okay, so it's what really makes it possible. The multiplexing or the combination through modulation is what really makes it possible for us to basically share a given medium. So wherever you are right now, like I said, you guys are sharing a medium with other groups of people, other groups of devices or nodes. But for the most part, you don't get to hear whatever their transmissions are. You just get whatever you are requesting for. And it's all made possible because of modulation using multiplexing implementations, okay, to make sure that we can carry all of you through a given medium of a given capacity. So coming back to the guy that said he was having a bad network connection, chances are the bandwidth or the capacity of the link that you are on, that you're sharing with other people, might be that choked, or maybe the modulation is probably not structured, well designed, well implemented, or has not been really calculated for properly to accommodate all the users that might be on it at a given point in time. Isaac, let me just go through this and then I'll come out to your questions. Okay, otherwise you're going to be behind. Okay. So these are the divisions that we have in diagram wise. So you have your frequency divisions, and that's a frequency one where you allocate a given spectrum or a given frequency spectrum for basically an infinite time. So this is what you reference to for the radio stations. So we have 4 users or 4 radio stations, and they've all been color coded. So let's say this is Joy FM over here, having the blue color. Its frequency is basically, it's no time bound, has no time limit. For as long as they keep paying the bills, it belongs to them. Nobody else gets that particular frequency with them. They don't share with anybody else. And then maybe this could be a Peace FM over here. This could be I don't know what are the names of other radio station, like Gold FM or Kasapa. What do you know Kasapa? I mean what are some of the names of the radio station? I don't know, but I can think of, Joy FM, Peace FM, Radio Gold, Anyway, so they allocated a frequency, and it's just for them for as long as they keep paying the bills. Now, on the time division aspect, this is what I mean by time is very constrained, and the frequencies are actually what allocated based on time lapse or time allocation. So if you notice in this scenario, Joy FM is given a particular time frame to operate. So this is that time frame. Once it expires, they lose a particular frequency and it gets reallocated to a different user somewhere else. Okay, and then once this particular time lapse as well gets reallocated. This is what you usually find within cellular transmission or data transmissions, because of the fact that the assumption is nobody is online 24/7. You're not making calls 24/7 to somebody, even though you might be in love with this new girl. You don't talk forever 24/7. I'm just being hypothetical over here, but you don't talk to that girl 24/7. What exactly could you be talking about? At some point, you're gonna get worn out, or you want to have a break and do other things else, with your time than just getting with that girl that you got. Anyways, that's just being hypothetical. Anyway, so you only have that time with time division. You only have a frequency allocated to you for a given time slots, and once that time expires, you lose it to a different user. Okay. So moving on. Now let's look at how you actually apply these in in implementation wise, using some calculations and scenarios. Okay, so we're going to go through some scenario where we have to apply circuit solution to address maybe frequency bandwidth for a given link capacity that we have. So let's move on to that particular scenario. The first scenario here is assume that you have a voice channel that occupies 4 kilohertz bandwidth. So you got some voice channels that occupies a bandwidth of 4 kilohertz. Now you need to combine them. You will need to modulate them or multiplex them into 3 voice channels so they can be passed through a given link. And that given link has a bandwidth of 12 kilohertz. So now let's put it into perspective. Let me open my drawing pad and then we can see if we can put into perspective over here. So drawing pad. So the scenario here was we had voice channel that occupies 4 kilohertz. Okay, and we need to combine how many of them? Is that 3? That was the question. We need to combine them to 3. Okay, so it was 3 connections. We need to combine them into 3. So this needs to be put together, right? Combine into 3 voice channels. Okay, so we can be able to modulate and multiplex it to pass through a given link. This is a link over here. So this could be your twisted pair cable link that helps with the transmission. And this link over here has got 12 kilohertz of bandwidth assigned to it. So the question is, if you were to, let me just erase this real quick. So if you wanted to send all these 4 kilohertz for each of these 3 voice channel, then it will be 4 times 3. This is kilohertz, by the way. And that will give you what? 12 kilohertz. So that 12 actually fits into the link that we have. So it means that this particular link can carry all the 3 voice channel of 4 kilohertz each. So that's very, very efficient. It means that we can accommodate all 3 voice channels on this 12 kilohertz bandwidth that we got. Okay. Now, in a scenario where the link that you use for the transmission that you need to combine multiple channels on is less than the accumulated bandwidth of various users, then you'd have issues with congestion. So assuming that, let's say this link here was actually less than 12. So let's say this is, this was say was 9. What do you think is going to happen? We actually need 12 kilohertz in total, but the bandwidth is only 9. So obviously, some of the users, some of these 3 voice channels might not be able to get a good enough bandwidth to handle their voice transmission needs. Okay? So when you're implementing a system like this, you want to make sure that the minimum bandwidth that you need for a given link to be able to accommodate all the voice channels that are going to be participating in a given transmission on our link must add up to that particular voice channels requirements that you have. So take, for instance, a telco company like MTN. Now, before they came to Ghana, they must have done an assessment to understand how many users have got cell phones in the country. Now, why do they need that? They need it because they understand they're going to be creating a link or a medium of transmission. And that link must be able to accommodate all those numbers of users that have got cell phones that are going to sign up on their network. So they can be able to accommodate them. If they don't do the assessment, then they wouldn't know how much bandwidth will be required for some of their cellular links to accommodate various users. And that's what happens sometimes when you have a scenario like this. You have, in this case, you have 4 kilohertz per device, per channel. And then there are 3 of them that you need to combine into one link. But the actual link you have only accommodates towards 9 kilohertz. Well, you actually have 12 kilohertz to accommodate for. So what happens? You have congested link because the minimum required bandwidth has not been satisfied. So ideally, you need at least 12 kilohertz of bandwidth to be able to address these 3 voice channels. Anything less than that will create what? A lot of congestion. I don't have network. My connection is slow. Yes, so once again, coming back to the guy with a question. This is one of the reasons why you're probably experiencing slow connection. So you're not getting to see my screen very well on your transmission. It's probably because you have maybe a link that you share with multiple users and it hasn't met the minimum requirement to accommodate for all the users that are being multiplexed or modulated onto that single link that's available to you guys to share. Okay, so you need at least a minimum of what? 12 kilohertz. Now, the question also says that you have to make provision for those 3 voice channels within these link of the frequency link that you have, or the frequency bandwidth link that you have. So in this case, that's from 20 to 24. Now let's go back to our diagram again and see if you can pick that one up. So if this were to be the link that you have, it allocate a section of it to start from 20 to what? 32. And you're supposed to fit those 3 voice channels into this. So this is what you have. This is what you basically, this is the link range that you have to fit these 12 kilohertz into. So what's the best approach to go about this? The best approach here, since it starts from 32, you can make it all 444. So you already is 4 kilohertz each for those 3 users, for all those 3 voice channels. So you can start from 20 to 24. That's the first one. So that's the first voice channel. The first. And the second can start from 24 to what? 28. And then the third channel can start from what? 28 to what? 32. So you've covered the range that you've been allocated to. So you notice that 1, 2, 3 voice channels, since it's 4 kilohertz each, the first one will take from what? 20 to 20. So from 20 to 24 here, it belongs to the first guy. From 24 to 28 will belong to the second. And then finally, the third one will be from 28 towards 32, and that'll be the third guy. So you've been able to accomplish the requirements needed to meet these 3 voice channel transmission needs. And that's what the question was really asking about. So the question, show the configuration using the frequency domain given with the assumption that there's no guard band in this scenario. And that's how you solve the question. So here's how you put it together in practical implementation. So you have your modulators combining the 3 voice channels. And the first one is taken from 20 to 24. The second one is taken from 24 to 28. And the third one is taken from what? 28 to 32. So once they go through this medium of 12 kilohertz, it can all be supported. So here you have from 20 to 32. And this is the 12 kilohertz band that you have to use for that transmission. Now, when the information, these three modulated voice channel gets to their destination, the transmission box that's carrying that's going to be linked to the various devices or destination nodes must separate these bandwidth or these voice channels back together to their respective channel ranges again, so they can be able to go to their respective destinations. And that's where you have what you call filters and shifting taking effect by what you call a band pass. So there's a band pass filter, which would take the multiplex or combined modulated signals and then refilter them into their respective bandwidth ranges from the 20 to 24, 24 to 38, and then 20 to 32 before it handed over to their respective users. So this is how you're able to basically not have confusions within a transmission, or we are all able to transmit information without any kind of issues, without hearing somebody else calling or somebody else's conversation on a given medium, all because of some of these implementations that have been put together to address some of these issues. So it really makes a lot of sense and a lot of streamlining to be able to have some of these implementations to allow circuit switching to accommodate for various number of users that are all using a given medium to transmit their vital information, whether it's a conversation, a hi message, or sending a data packet, a WhatsApp, a text, or whatever. All these are needed to be able to make that possible. And then based on those calculations, we're able to deduce this approach to configuring our system to accommodate these specific users that we have. So in this case, it's just for 3 voice channels. You might have scenarios where you have, obviously, this is just more or less an ideal simplistic scenario over here. Obvious in real life implementation, there are thousands and millions of us. So you can imagine if you were to be the engineer, the telecom engineer, the network engineer implementing it or configuring the system to address maybe thousands of nodes, like or millions. I think MTN has the largest subscriber units, right, in Ghana. So you can imagine what the engineers go through doing the calculations for configuring a system that will accommodate all of those users within a given locality or a given region or a given place that they want to provide service to. They go through a lot of calculations, complex ones with all kinds of, accommodations. They have to accommodate all kinds of scenarios, maybe line of sight issues, kind of infrastructure within a particular location. For instance, if in the cities where you have sky-rise buildings and how high-rise buildings made of metal and all kinds of thick concrete material, you have to kind of accommodate for all kinds of things. Must be factored into a design to make sure that you can accommodate all of these thousands of users that you might be handled on your links at any given point in time. Okay, so the engineers really do a lot of work before they actually get to the implementation. But this is the basics of it, okay? Are we good? The second question, so that's on the second question. I have 2 questions over here for you guys to go through. So the second question here is, you have 5 channels, each having 100 kilohertz bandwidth. Now you're going to multiply that together. So you have 5 channels carrying 100 kilohertz each bandwidth. And you're going to multiply all of that together. So you need to combine all of that together. The question it asks you here is, what is the minimum bandwidth of a given link that could accommodate all of these 5 channels of 100 kilohertz each? And on top of that, you have to make provision for 10 kilohertz of what? Guard band between the channels so you can prevent interferences. Now, the previous question, there were no guard bands. It was assumed that there were no guard band, okay? But in real life, you're going to need the guard band. Otherwise, interferences will come, because when channels are too close to each other, they will create what you call a crosstalk or interferences. So in this scenario, being a bit more practical, they tell you that you have 5 channels, each one having 100 kilohertz per bandwidth. And then you need to basically multiply all of that together. Okay? But in a combination, you need to factor, make provision for what's 10 kilohertz guard band. So let's see how you go about that calculation. So let's go. So it was 5 voice channels, right? 5 of words, 10 or 100 kilohertz voice channel, right? Or yeah, voice channels, right? So you got 5. So if you do the math, it's going to be 5 times 100, which gives you 500 kilohertz. So you need, so to get you started, you need 500 kilohertz as the beginning, even beginning stats for your link that you're going to use for that particular medium transmission. So this is our link again. So first of all, we need 5. We want to make sure the minimum to start out with is what? 500 kilohertz. This link has to have a bandwidth of at least 500 right now. We've not even factored in the what? The guard bands yet. Now let's try to calculate for the guard bands. The guard bands it was 10 kilohertz, right? And we have to fuse into each of those channels. So we have there are 5 channels, right? And we need to fuse this 10 kilohertz into these 5 channels. So how many technically guard bands do we need? Well, if you were to draw a line and try to put together all those 5 channels. So this is channel 1, channel 2, channel 3, channel 4, and channel 5. Okay. So the guard bands are the allowances between channel 1 and 2, 2 and 3, 3 and 4, and 4 and 5. So these are the gaps. So these gaps over here are going to be your guard bands. So how many are there? There's 1, 2, 3, 4. Actually 4. So we need 4 guard bands. So 4 times 10 kilohertz each will give what? 40 kilohertz. So that means we need to add that 40 to the actual bandwidth of all the frequency channels that we have, all the 5 frequencies we have. So in actuality, the minimum link to support all of these 5 channels would actually be 500 plus 40, which would give you 540 kilohertz. So the minimum you're going to need to accommodate, so the minimum bandwidth to accommodate for all those 5 is at least 540 kilohertz bandwidth. Okay. I don't know if you guys got this, but let me go through the diagram over here, the solution diagram, so you guys see how it works out. So you got so as I indicated, you have the 5 channels, 1, 2, 3, 4, 5 in different colors, and then they have the guard bands in between, the allowances in between it, and we realized that it had to be 4. 1, 2, 3, 4. So 4 times 10 will give you 40 guard bands. Okay. And then you add it to the 5 times 100 for each of the 5 channels we have. And that's how you get your 450 kilohertz. Okay. These are simple math. These are nothing complicated, more or less GSS math. Once you understand the concept behind the module or the combination of various voice channels and their respective bandwidth, and the rest becomes just simple GSS math. Okay, so I don't think you guys should be having challenges with questions like this on an assessment, either a quiz or a midsem or a final. It should just be basic. If I put twist in there, the twist is just to get you to think, okay, to see, because I'm giving the basics over here. Obviously, if I were to repeat the exact same thing in an exam, you guys are going to score 100% on it. So I'll put a twist in there. And the twist is basically get you to think. Okay. And obviously, it's going to be twist in your assessments. It's not going to be straightforward like this. I'll put some twists to see how well a student understood this particular concept of splitting and modulating circuit switching transmission to address very specific transmission needs. Okay. Great. And then various applications. We have FM. So I've mentioned about that. AM radio stations, FM radio stations, and TV channels or TV stations. So those are where we find a lot of these circuit switching applications within more or less analog transmissions. But today we have what you call digital transmissions or digital applications. And that's where we switch to the next slide, which is packet switching, or the next switch network, which is packet switching, which is purely digital based on data being sent in discrete portions with what fixed value of either 1 or 0. So now let's delve right into that as well and see how well we can understand it as well. So the next one is packet switching. And with packet switching, it's more or less a bit of the opposite of circuit switching. So with packet switching, there's no dedicated streaming. And usually your data are not like streaming continuously like voice does. They're actually data that are stored and forwarded. So hence, in terms of their stream, they've been divided into what packets because of the fact that they only require non-synchronous transmission, or they don't require a dedicated path or shared resources for their transmission or reserve resources for their transmission. They need to not have that dedicated path, but instead they can share a network resources and use those divided packets to address a number of specific route needs before they actually end up at the final destination. Like for instance, an example would be you accessing Facebook. Facebook and most of the social media content, they don't stream live. They are all information stored on servers and you access them. A good example is your friend's profile, the pictures they've uploaded on social medias. They are stored on servers and then you get to what? Access them. So they are not a live transmission. They are just stored somewhere and then you log onto those platforms and you access them. So in that case, we don't really need that dedicated path or constant shared medium resource or bandwidth for that particular transmission. And that's why they broke some of these data stream within packet switching into what you call packets. So they divide into packets, and then they basically pass them through different path, different dedicated path, or sorry, different non-dedicated path across the internet. And then once they all come together, they are regrouped and then handed over to a given resource that needs it. So for instance, using the same Facebook scenario, if you were to click on somebody's social media profile or Facebook profile, the request can actually go through a number of routes on the internet, a number of paths. But the key here is, let's assume that a request one request actually was broken down into 5 packets. Okay, so there's a request to Facebook and it was actually broken down into 5 packets within packet switching. Then all these 5, once they hit their various transmission nodes like a router or a switcher, it's the job of those routers to figure out which path to run all those 5 packets through en route to their destination. So it can basically say, okay, maybe packets 1 and 2 go through path 1. Packet 3 and 4 go to path 3 or path 2, and then the rest go to a different path. But before all those packets get to the destination, the node that handles the final destination has to basically identify that the packet's been sent. If it got, say, maybe packet 1 and 2 first, the header information attached to those packets must tell the router or that switch or that network node that the information then to be requested, that Facebook profile that this particular user requested for, is actually contained within 5 packets. So if it has for the first 2, it has to wait for what? The rest 3 to come through before it hands it over to what? Facebook, and pick the request and then send it back to you to view on your phone. Now, all of these happens in what? Nanoseconds or microseconds. So for you and I, we don't really see it. But for the most part, those requests might have gone through thousands of mileage. I might have crossed through continents, traveling through, various cablings, fiber optic, twisted pairs, and other mediums. Before getting to Facebook and then picking the resource from that particular social media profile you picked, and then hands it back to the network, and then heads all the way back to you for that round trip. And it all happens in what? Microseconds. Once you click, it just shows up. But it has gone through a number of things, a number of routes. But since electricity is what carries a chunk of our data information, it travels at the speed of light. So in microseconds, we're able to get some of these requests. But in the back end, they have traveled thousands of miles. That request, that Facebook request or social media links or pictures or reading or text that you're reading might have traveled thousands of what? Distances or millions of distances through the internet of interconnected, devices and mediums just to get to you. So you need to start appreciating what you got. The fact that you have a device that can just, once you click on something, it just works. Once you click on a profile, it just loads. Once you send a WhatsApp message, instantly the other person sees it. Once they're online, they see it, they receive it, they read it, and they reply back. And it happens so fast. We good, guys. So some of these are very, very, interesting stuff. And this is what we need to understand. Because once you understand this, you're able to appreciate the technology you have in your hands. You can see how much engineers have thought through and be able to address a number of challenges to make that information get to you at the speed of light. Anyway, so packet switching does that very, very